Hello everyone. In this presentation, I will be discussing Earth observation for climate change monitoring, a comprehensive survey. I am Ajit, and today I will talk you through how satellite Earth observation supports climate science using sensors, datasets, and the modern analytical methods. So, in the climate change cannot be monitored using local ground stations alone because they offer limited spatial coverage. So mm, that's why the Earth observation satellites provide global, continuous, and long-term measurements that can help us understand environmental changes over time. So the survey summarizes EVO techniques, datasets, and machine learning approaches that are widely used today in climate monitoring. So why Earth observation? The, the Earth observation is essential because the traditional ground measurements are limited to specific locations, and the satellites, on the other hand, deliver multi um, spectral and hyperspectral data, which is a long-term archives over 30 years and continuous global coverage. So the EU supports key climate application, including land cover change and temperature and variation of greenhouse gas tracking, and like ice and ocean monitoring, like the strokes. So the Earth observation block, the EVO sensors overview. So in this, EVO sensors are broadly divided into passive and active categories. So passive sensors include the multispectral optical sensors like Sentinel-2 and the Landsat 8. The thermal infrared sensors such as MODIS and VIRIS and the microwave radiometers. Active sensor, active sensor like include the synthetic aperture radar and LIDAR, which is send their own energy signals to capture detailed surveys information. So the sensor type observe the different aspect of Earth systems. So the key data sets in the climate monitoring, which is different EVO data sets provide a different strength. The Landsat offers the longest continuous land monitoring data sets since 1972, and MODIS provides daily global observation used for vegetation and temperature monitoring. So Sentinel-1 radar helps um, with crop mapping and soil moisture analysis, while Sentinel-2 optical data capture the high resolution and the cover of details. And ERA5 is offer global climate reanalysis for atmospheric and environmental monitoring. So in the atmospheric change monitor, there's many satellites monitor atmospheric changes like especially the greenhouse gases um, like CO2 and methane. The OCO provides a precise CO2 measurement, while TROPMI maps pollutants such as NO2 and CH4 and the ozone. These datasets help us detect industrial emission and the urban pollution patterns. A common equation used for this equation, which links the radioactive force with the CO2 concentration changes. So, in this case, the UO plays a major role in land cover and vegetation monitoring. It helps detecting deforestation, droughts, and the crop stress, and also the forest degradation. So, one of the most important vegetation indication is NDVI. So, which is uses the near infrared and the red bands to measure the plant health. You can see the examples like in the pictures I have uploaded. So the healthy vegetation shows high NDVA and the stressed vegetation shows the lower line. So and glaciers and the polar regions are the highly sensitive to the climate change. So radar from Sentinel-1 used to track ice movements and the thickness, while optical data monitors survey melting. So ICS at two laser ultimately helps measure elevation change and glacier the massive balance. So long-term satellite observations are clearly showing decreasing the Arctic Sea ice and extend over the past decades. Sorry for this image we have covered. Sorry for that. And the ocean monitoring, it's like the ocean, it's absorbed the large amount of the heat, like you can see the large amount of heat, and it plays a major role in the Earth climate system. So, like the satellite like MODIS and AVHR measure the sea surface and sea surface temperature, while adjacent-free altimetry missions like track global sea levels rise. So, ocean color sensor help estimate help estimate the um, chlorophyll concentration, which is linked to marine ecosystem. The SST anomaly equation compare current sea temperature with long-term averages. You can see there is machine learning in Evo for climate. The machine learning greatly enhanced the analysis of Evo data. So the classification models like random forests, like SVMs and the CNN, help identify the land cover types like time series forecasting models such as like LSTMs and the transformers predict environmental changes. Okay. What change detect on this technique was like image differencing. SAM is the network improve accuracy and help the automate monitoring tasks. So in the deep learning has like becoming extremely and powerful for interpreting the satellite imagery. Like CNNs are widely used for future extraction and the classification for the task. So UN like uh, architectures perform the precise segmentation for useful for an urban mapping and vegetation of extraction and like the disaster mapping. So the hybrid CNN and LST, uh, these models are like analyzes both spatial and the temporal patterns, like making them therefore suitable climate studies. The the climate change application, like the Earth observation, uh, like support a wide range of climate application. For example, like including monitoring deforestation in the Amazon or analyzing the urban heat island effects, studying glacier retreat, pred- that predicting the wildfire risk, and we can track the air pollution levels. Like satellite data allow us to observe both gradual and also like sudden environment. So the you can see the differences between that captured from the satellite images, like uh, before and after. So how it is looking like. So challenges in global climate monitoring, which is like despite major progress, EVO still faces challenges. In this case, the cloud cover affect optical sensors, while massive data volume require a strong computational resource. In this, different sensor produces the mm, heterogeneous data that must be harmonized, and the calibration differences, which is limited ground truth, can reduce the accuracy. In this overcoming these challenges in the overcoming period, it is essential for reliable climate monitoring. So, the future direction. So, the future of EVO efforts will focus on the hyperspectral missions with more detailed spectral information, which is improved fusion of multi-sensor data and advanced AI-driven change detection system. We also expect near real-time climate alert systems and stronger integration with the ground sensors, the base ground sensors. These developments which help create more accurate and timely climate insights. So finally, we are in the conclusion, like to conclude, the Earth observation is fundamental to understanding and also the monitoring the climate change. So advanced in the machine learning and the deep learning have greatly improved the accuracy and the speed of view analysis. The long-term data sets from missions like Lancet, Sentinel, and Moody's enable us to build the predictive climate, which is models and support globally for the climate policy. So yeah, thank you.